Good morning. So I want to talk about software engineering, and maybe not in the way in which you think. So I spent the early part of my career with job titles like junior software engineer and later senior software engineer and things like that. And then through the middle part of my career, I started working for organizations that didn't really like the term engineering. We tended to think it was the wrong term. We talked of ourselves as software craftspeople and had job titles like software developer. I once worked in a place where we had several grand wizards as part of our development staff, but we called ourselves different things. And then in the latter part of my career, I worked on some projects that were genuinely deeply demanding technically. I built one of the world's highest performance financial exchanges. And while we were doing that, it was while I was in the middle of writing the Continuous Delivery book. And so we were applying those kinds of principles to developing this difficult software. And I started to think that what we were doing was closer to a real engineering discipline. And so that's kind of the theme of my talk today. I think that when we think about engineering, software engineering in particular, at least if you're anything like me, the thing that springs to your mind is a picture, something like this. And this is not software engineering. This is to software engineering what a soldering iron is to electrical engineering. It's a tool. It might be a good tool, it might be a bad tool, but it's only a tool. This does not define what engineering means. So this is not helping us kind of understand what it is that we need to think about if we want to start thinking in terms of engineering. One of the things, I've been thinking about this stuff for a few years now, and I have lots of different conversations with people in different places, in bars and on Twitter and all that kind of stuff. And so I get involved in these conversations, and somebody said something to me a little while ago that kind of resonated with me. And they said that if we were able to come up with sort of principles for an engineering discipline in software development, they would probably be as true in 100 years' time as they are today. And that kind of landed with me, because I think that's probably true. If you think about what really defines engineering in other disciplines, it's not the kind of latest tools or techniques or ideas, it's the founding principles. And that's the stuff that I really want to talk about. We often talk about, when we talk about software development, certainly, but also engineering, we often sort of confuse the ideas of process and so on with kind of the deeper meanings, and we come up with things like this. This is Scrum, a picture of Scrum. Any idea how many times the Scrum documentation mentions the words code or software? I'll tell you, it's none. So Scrum is an excellent project management approach. It's really effective, but it doesn't say anything about engineering. It doesn't really tell us about how we need to think about that sort of stuff. So this doesn't work as a definition either. And then we get onto the stuff that the companies that I worked in the middle of my career found fashionable, the idea of software craftsmanship. And I think there's a lot of good stuff in the ideas of software craftsmanship. I think that it happened in response to some of the mistakes that we made in terms of approaches to software development. Mistaking the software development process as a problem in production was one of the things. So mostly, if we're building physical artifacts, if you're building cars or computers or even chairs or something, the problem of reproducing those things, productionizing the original design, is a difficult problem. For us, that's not the case. For us, once we've got the design right, we can copy it as many times as we like, essentially for free, because it's just a stream of bytes. And so production isn't our problem, and yet what we've tended to do over the decades of software development is that we've tried to apply production line style thinking to software development. So thinking in terms of it being more like a craft and thinking more about the kind of the creative part of the process is a good step forward, I think. But nevertheless, this really doesn't define what software engineering means, as a discipline. I think it's a useful model that you can decompose production of things, the creation of things that human beings have made, into three phases. Originally, for much of our history as a species, everything that we built was the fruits of a craft-based approach to producing things. That's how we made everything. And then around about 150 years ago, we started doing some other things. We started applying the techniques of mass production to make the production process more reliable, more efficient, and have higher quality. And that worked. The first example of that was the production of rifles in the American, or armaments in the American Civil War. And one of the horrific things about that war was that it was the first really mechanized war. So we were able to build weapons that were able to kill people faster and more efficiently off the back of this improved production approach. There's an interesting story, a nice story, if you can have nice stories about such a horrific event. The man that wanted the contract to build the rifles for the northern states in the American Civil War went to Congress with a bag full of components, and he tipped the components out on the floor of Congress. He asked the congressman to select components, and from the components that they chose, he built a rifle. That was the first time in human history where that was possible. The standardization, the quality of the pieces, all of that sort of stuff. That was the first event where just that simple task was possible. Before that, you'd have had a handcrafted device that was built from scratch. If you broke your rifle, you'd have had to probably go to the same gunsmith that made it originally. And when you bought your gun, you'd probably be given a mold for the bullets because each bullet was different for every gun, and so on. So craft was kind of superseded by mass production because it was able to introduce standardization and all these sorts of things. At the end of the Second World War, Edwards Deming went to Japan, and it kind of helped them take some Japanese cultural ideas that were already there, but amplify those. And the fruits of that thinking gave birth to what we would now think of as lean production techniques. And lean production is kind of a step on from mass production techniques. It allows us to kind of do pull-based systems, just-in-time delivery of ideas and materials, to be able to deliver things. You kind of pull the stuff down the line rather than push it along the line. And it's more effective. It's demonstrably more effective. So where are we as an industry? Where is the software development industry? I think, as you will have gathered from what I've been talking about, we are not a mass production industry, and we never will be and never should be. Mass production is the wrong model for the kinds of problems that we have. We don't really have production problems, we have design problems. So I think that we are a craft industry, and one of the hallmarks of craft industries is that the quality tends to be variable. It tends to be a little bit up and a little bit down, depending on the quality of the individual. I think that we have as human beings, we have a fond regard, we have an emotional attachment to the idea of craft-built things. We like the idea that human-made things are nice. If we're very wealthy, maybe we buy cars with hand-stitched leather seats and all that kind of stuff. But for a moment, I would just like to pose a question. Can you imagine a craft-built version of one of these things? That's a kind of crazy idea. Even the prototype of something this sophisticated required deep engineering. It required not just deep design engineering, but deep production engineering in this case, to be able to build just the prototypes. Part of the cleverness is to be able to build prototypes that you can kind of learn from and so on when you're building something as complicated as this. The precision with which this is built is off the scale compared to the precision that a human being can exert without engineering principles, thinking, and the amplification of skills that engineering brings. I think that where we should be shooting for is probably closer to this, sort of using some of the ideas of lean production, but I think it goes sort of deeper than that as well. When we start applying some of these principles, what we see is quite dramatic. We see significant improvements in the quality of the things that we build, the rate at which we can produce these things, the productivity of our approaches, the utility, the response of our users to the things that we create goes up. We're able to better evolve and develop products to fit user needs. All of these things are amplified, and not just by small amounts, often by close to significant fractions or orders of magnitude of what went before. And that's kind of what you'd expect if what we were talking about was genuinely engineering. The bottom line here is the bottom line. Organizations that practice these kinds of disciplines make more money than organizations that don't. And again, that's kind of what you would expect if we were able to start to think in terms of what engineering, practice something that was really engineering in our discipline. As I said earlier, I get involved in lots of conversations about engineering these days as a result of talks like this and some of the things that I write about. And I get involved in a surprisingly large number of conversations about bridge building. People say, oh yes, but software development isn't bridge building, is it? And well, no, of course it's not bridge building. But bridge building isn't what we think it is either. If you are building the 900th suspension bridge that's exactly the same as all of the other 899 suspension bridges that went before it, that's a completely different kind of problem to if you're building the first kind of bridge that's ever existed. The first problem is a production problem. You've probably got a bill of materials that you've developed over the time that you can just lift off the shelf. You've probably got a Gantt chart, a project plan that tells you how to deliver all the materials and when you need them in your project lifecycle to do it. And there's probably a few variables that you can plug in and get a good answer. If you're building the first kind of bridge for the first time, that's profoundly different. You're going to be building test pieces and models. You're going to be putting them on shake tables to see what happens in an earthquake and wind tunnels to see what happens when the wind blows, and you're going to be measuring all sorts of different things. It's going to be much, much more experimental. So bridge building first isn't what we think it is. The other way in which bridge building is kind of not the right model is that bridge building isn't the only kind of engineering. Bridge building, the engineering around production, building those sorts of large industrial structures is different to the engineering for building things like houses, like building aerospace systems, like building electronic systems. Chemical engineering is not the same. All of these disciplines have their own unique characteristics, but all of them have some kind of common framework on which they're built. And that's the stuff that I'm kind of interested in. The other way in which engineering is not the same is it's not the same at different scales. So here are two engineered structures. You can bet that if it was an IKEA shed on the left-hand side here, then it would have been engineered to a fair degree to make sure it used the minimum amount of components so that it could build cost effectively, to deliver value, and they would just be stressed enough to hold up the roofs and all that kind of stuff. The other building on the right is unique. It's the tallest building in the world. When they built that, again, they would have been building models of it, computer models of it, doing finite element analysis, measuring it on earthquake tables and things like this to try and figure out what it would take to build a building on this kind of scale. So engineering is different at different scales. And that's obvious when you look at things like buildings. It's less obvious when you look at software. It's not to the man in the street or the consumer of our software, it's not absolutely self-evident that the amount of effort and engineering that goes into building software, I don't know, in a flight control system or a pacemaker is different or should be different to the amount of engineering that goes into building a sweet shop online. But nevertheless, it is. The level of rigor that goes into those things is going to change with the nature of the problem. But again, despite that, there are going to be common principles that are shared in both of those undertakings. So let's start digging into definitions a little bit. And if you kind of start thinking about what engineering really means and looking up descriptions, here's a definition from Wikipedia. Engineering is the application of mathematics, empirical evidence, scientific and economic, to solve scientific, economic, and social blah, 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 blah. But there's a bunch of words that tend to crop up over and over again. So here is my working definition for what it is that I'm talking about in this context for the rest of this talk. So engineering is the application of an empirical, scientific approach to finding efficient solutions to practical problems. I think all of the words in that description are accurate. And when I talk about efficient solutions, I mean efficient in terms of the cost effectiveness of the production, as well as efficient in terms of the performance of the things that we build that's appropriate to their need. So we need to think about those sorts of things if we're going to start applying engineering to do these things. And I'm challenged by the kind of conversations that I have started to come up with some ideas that I think feel to me as though they are profound, that they are common against any kind of engineering that we could consider. I can't imagine anything that we would consider software engineering in our discipline that doesn't exhibit these 5 characteristics. Fundamentals of an engineering approach. It's going to be iterative. We need to be able to do things so that we can learn more quickly. It's going to employ feedback. We need to gather the data so that we can learn effectively. It's going to be incremental. You don't build a complicated system by building the whole thing in one step. You build a complicated system by first building a simple system. And then it's going to be experimental. We need to be able to try ideas out. We're not going to know the answers to problems before we've actually started to address the problems. And it's going to be empirical. We're going to learn from the real world. We're not going to be able to perfectly predict the outcomes. So let's go through those a little bit. So iteration, the act of repeating a process. Oops, sorry, clicked too quickly. The act of repeating a process to generate an unbounded sequence of outcomes, or with the aim of approaching a desired target or goal. Iteration is vitally important because it means that we can learn, we can react to what we learn, and we can adapt to what we've learned. And that gives us this opportunity. So the more frequently we can iterate, the more regularly we can learn and improve our understanding of the problem domain, the technologies, the team dynamics, all of those things. It allows us to steer towards a goal. You don't decide that you're going to drive from Madrid to Barcelona by taking a bearing and kind of working at the time and just steering in that direction. What you do is that you do something more adaptive. You're going to start on the road. You're probably going to be looking at Google Maps and seeing what the traffic's like, and you're going to be adapting your route depending on the traffic. That's how you get to somewhere. That's how you make things work. You break it down into a series of smaller incremental steps, and that allows you to learn more effectively. The other thing about this is it gives us a route to continual improvement. It means that we can start off building something simple, maybe even crude as a first step, and we can refine it over time and make it better and better. And what that does, it gives us the ability to enhance our own skills and learning and experience so that we become better, our teams become more effective. One of the hallmarks of the kinds of teams that adopt these sorts of disciplines that I observe is that they tend to get better and better and better over time rather than slower and slower and slower over time. Feedback. Feedback is information about actions returned to the source of the action so that we can kind of adapt. Feedback is vitally important. It gives the opportunity to disambiguate myth from reality. It gives us the opportunity to respond to what we're doing and understand the impact of our choices, whether they were good ideas or bad ideas. We need to focus on making sure that we have the right sort of information returned at the right point regularly and frequently so that we can keep this idea of learning going. I've come to believe that software development is a process that is fundamentally grounded in only 2 things. We need to be effective at learning, and we need to work in a way so that we can kind of fit ideas inside our heads. So ideas of modularity and so on are important, but focusing on learning and optimizing for learning are foundational in what it is that we need to do if we're going to do really high quality work. This is a schematic that I tend to use and have used for many years to describe continuous delivery, my favorite approach to software development and engineering. And it's grounded in feedback. At the outside, we've got the idea, you have an idea, get it into the hands of users and figure out what they make of it. At the inside, we've got the fast feedback loop of test-driven development. And in between, we've got other kinds of feedback loops. It's completely a feedback-driven approach. And so I think it's profoundly important to our ability to move forwards. We also need to think, as well as being iterative and feedback driven, we need to also work incrementally. Incremental evolutionary design, continuous design, evolutive design, incremental design is directly related to any modular design application in which components can be freely substituted. Modular design is really important. As I said before, we don't build a complex system by planning it all in detail and building the whole thing in one big step. That doesn't work. My wife, who's at the back of the room somewhere, says that I'm a serial nerd, and she's wrong because I'm a parallel nerd. I can be a nerd on multiple fronts at the same time. So I'm going to demonstrate that by talking about one of my nerdisms, which is aviation and the space program, while demonstrating ideas of software engineering, I hope. So this is the picture of the Saturn V, the spaceship that took astronauts to the moon and returned them. And this was a modular system. This was a highly modular system. And that wasn't how they planned it originally. That wasn't what they thought about at the time when they were building it. This part of the spacecraft solves the extremely difficult problem of getting the rest of the spacecraft from Earth into Earth orbit. The top part of the spacecraft is made essentially of 4 components. Here are 2 of them. This part is the command module. Its job was to get the astronauts from Earth orbit back down to Earth again. And this is the service module. And the job of this part of the spacecraft was to get the whole contraption from Earth orbit to the moon and from the moon back to Earth orbit again. And then we've got the lunar lander part. That's 2 components as well. The top part was to get 2 astronauts from the surface of the moon standing up in their spacesuits from the surface of the moon back into lunar orbit, where they could rendezvous with the command module and the service module. And the bottom part was the lander part that sort of took them down and landed them on the moon. As I said, when NASA first started thinking of the Apollo missions, this isn't what they had in mind. What they had in mind was much more like kind of a kid's cartoon space rocket that took off from the Earth, flew all the way to the moon, landed on the moon, they got out, walked about, and it took off and flew all the way back. That's enormously expensive in terms of the energy budget to be able to deliver all of that payload to the surface of the moon and to bring it all back. But it also means that it's inflexible. It all has to work or the astronauts die. In this model, in this more modular approach, you can be cleverer. You can recompose the spacecraft in different ways. In fact, that happened when the Apollo 13 disaster happened and the service module essentially blew up and lost a lot of their consumables. They were able to reconfigure the spacecraft and use the lunar module as essentially a lifeboat to get the astronauts back to Earth. That wouldn't have been possible if this hadn't been built as a modular system. The other part of this is that as a modular system, it allowed them to farm out the construction of the system to different groups of people. In fact, different organizations built different parts of the spacecraft. And that meant that they could move more quickly and in parallel. I've used 2 different words that in English are very similar, so I'm just going to pull those, just show the difference between those. And these pictures are taken from my friend Jeff Patton's book on story mapping, which really beautifully describes the difference between iterative and incremental. An iterative approach is this. You're going to start out with a rough sketch of what you want, and then you're going to fill in the detail and the quality over time until you end up where you want to be. An incremental approach is the modular approach. You're going to do pieces of work to whatever level of quality, and you're going to assemble the whole over time, piece by piece by piece. I think that anything that we could consider to be an engineering discipline is going to require both of these. We need to be both incremental and iterative to be able to achieve anything substantial. We want to be experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect, demonstrating what outcome occurs when a particular variable is manipulated. I'm going to explore my nerdism again, and it's a nice coincidence that part of the theme for Codemotion this year is the 50th anniversary of the moon landings. So I'm going to use the moon landings as an example again. So in 1961, President Kennedy stood up in Congress, in American Congress, and said, we're going to send people to the moon and we're going to bring them back again by the end of the decade. And everybody in NASA went, because they had no clue how to do that. When he said this in 1961, this was 2 weeks after Alan Shepard was the first American into space. Alan Shepard was a ridiculously brave man because they were in competition with the Russians at the time. They were kind of rushing the program. And the Russians had already done several successful manned space launches, so the Americans felt they were in catch-up mode. So what they did was that they strapped Alan Shepard essentially into a tin can on top of an intercontinental ballistic missile. These missiles, the Redstone boosters, were blowing up on the launch pads all of the time. They weren't very reliable. So they strapped Alan Shepard onto the top, fired him 100 miles up, and he parachuted back down again. That was the first American space mission. 2 weeks later, Kennedy's saying, we're going to the moon. So Kennedy's kind of done what senior people often done. He's kind of expressed a vision. He said, let's go to the moon. Let's go to the moon. I have no idea how to do that. I'm a politician. You're smart. Figure it out. And all of the people in NASA are kind of stuck there thinking, what are we going to do now? Somebody once said to me, is this the most expensive user story of all time? And I think it's a candidate. I think it could well be. Here are pictures of all of the things that they didn't know how to do at the time when Kennedy made his speech. This is pretty much all of the things that you need to know how to do. So they hadn't really got launches sorted, as I said. They were blowing up on the pad all of the time. They hadn't got multi-stage vehicles working yet reliably. They hadn't got the splashdown phase reliable. The next mission after Alan Shepard's, the capsule sank, leaving Gus Grissom nearly drowning in his space suit in the middle of the ocean. Nobody had yet done spacewalks. They hadn't really got spacesuits that operated in a vacuum. They tended to inflate, and when the first people did do spacewalks, they did do that. The spaceships inflated, and they nearly died because they couldn't get back in the spaceship very well. They hadn't got the mission control stuff sorted out. They were refining all of those things. Nobody docked 2 spacecraft together yet in space. All of these things were things that they had to learn how to do. So where do you start when you have a problem on that scale? So one place where you start is you hire some really, really smart people. This is Margaret Hamilton. She was the first person to use the term software engineer. She was the first person to think that what she was doing might be a form of engineering. Margaret was the lead for the spacecraft control systems team. And you know, that's one thing that you do. You get these people that are really brilliant. But then the next thing that you do is that you need to start thinking about the problem. So here's the problem. This is the Earth-Moon system. Except this is a kid's storybook picture of the Earth-Moon system. This isn't really the problem. This is the problem. This is a picture of the Earth-Moon system to scale. At this point in history, no human artifact had been more than 1 pixel away from the Earth. So problem 1, how do you get anything from all the way over there to all the way over there? That's the first problem. You can kind of imagine the conversation the next day after Kennedy stood up in Congress in NASA. You can imagine all the NASA engineers getting around and talking about this and saying, what are we going to do? He's just said we're going to do it in 9 years' time. How are we going to do that? Oh, no. My brother-in-law's got a car showroom. We could all get jobs there. No, that's no good. How are we going to do this? I know. Let's build a spaceship, put 3 astronauts in it, send them to the moon and see if they come back. No, that's not going to work. Waterfall is not the answer for this problem. Hold on, I've got a good idea. Oh, no, we don't have to put astronauts in the spaceship. We could automate the spaceship. We could send it to the moon and bring it back without any astronauts. We wouldn't kill the astronauts, and we'd probably keep our funding for a bit longer. That would be good. No, it's still incredibly hard, though, isn't it? Sending the spaceship all the way to the moon. Hold on a minute. We don't have to bring it back. We could just send the spaceship to the moon and land it on the moon, and we'd learn loads from that. And then it would simplify the problem. That is a good idea. What does landing on the moon mean? Well, he doesn't have to survive the landing on the moon. And that was the job of this space program. This is a real space program. This is the Ranger series of spacecraft. These were literally spaceships as bullets used to see if you could hit the moon. This is lunar target practice. So how did that go? How did that work out? Well, the first mission, as I said, they hadn't really got the launch system sorted yet. The job of the first mission was just to get into Earth orbit. The spacecraft blew up on the launch pad. The second one, just to get into Earth orbit again, the spaceship blew up on the launch pad. If you've ever worked in a big project, the next bit might amuse you. So they've failed to get both of these things, they failed the objectives of the first two missions, but they have learnt stuff. And so they said, well, the third mission's supposed to go to the moon, and we haven't been able to get into Earth orbit yet, but let's go for the moon anyway. So that's what they did. They managed to get it into Earth orbit. They did the deorbit burn, fired the spacecraft off towards the moon, and it missed the moon entirely. The third one, it worked. They got it into Earth orbit, they did the deorbit burn, they fired the spacecraft off, and the spacecraft died. They lost all communication with the spacecraft, but they managed to track it from ground-based stations, and they saw that it actually did hit the moon. So that's a win. The fifth one missed the moon again. The sixth one, it worked. It hit the moon, they got some telemetry back, but the cameras failed, so they didn't get any pictures. The seventh one was a success, the eighth one was a success, and the ninth one was a success. So you're NASA in the middle of the Cold War. Essentially, this is the focus of the aerospace industrial complex. You've got access to the smartest minds in the Western world. Imagine yourself being at the end of the phone and say, hi, it's NASA here, we're having some trouble. Would you like to come and help us? You'd be on the next flight. It'd be a wonderfully exciting experience. You've got access to the brilliant people. Where do you start? You don't start by planning the whole thing in detail. You start by carrying out experiments. You begin learning. That's what you focus on. You focus on learning in the direction of travel that you want to go in, the things that, your ultimate goal, but it's all about learning. There were millions more experiments than this. This is just an entertaining, interesting program to talk about. But you could look at almost any aspect of the development of the Apollo missions, and it was all about experimentation and learning. Experimentation is humanity's best problem-solving technique. It's the thing that differentiates our high-tech civilization from the agrarian kind of craft-based civilizations that went before it. I want to show a little example. Here are two orange dots, and I would like you to join in. So I'd like to have a show of hands if you think that the dot on the left-hand side of the screen is bigger than the dot on the right. Nobody. I'd like to, if the dot on the right-hand side of the screen is bigger, show of hands. I think you might have seen this before. If you think they're both the same, you're right, it's a visual illusion. But how can we tell? Well, we can carry out an experiment. Here's my experiment. They are, in fact, the same size. Have you seen this one before as well? Okay. So hands up if you think this line on the left-hand side is shorter. Is longer. Hands up. Hands up if you think that the line on the right-hand side is longer. There's a smattering of people, a handful of people. Hands up if you think they're both the same. Okay, everybody with your hands up, you weren't paying attention. You can't tell without experimenting. The line on the right is longer because I made it longer. Just guessing isn't good enough. Just guessing is not sufficient. We need to measure. We need to have a hypothesis. We need to understand what's going to happen. And then we need to measure. Being experimental is really vital in terms of really doing high-quality learning. It's the best problem-solving technique that we have as a species. Finally, the fifth of my attributes of software engineering in this category is being empirical. Based on, concerned with, or verifiable by observation or experience rather than theory or pure logic. Being empirical is really important. It means that we can kind of start learning from our experience. We can kind of start making evidence-based decisions rather than making progress on the basis of guesswork. We also need guesses at the start of our process, but we need to be able to start using evidence. We can start being more scientific. We can start applying the ideas of science to our problem-solving techniques. We can start disambiguating mythologies from truths and understanding what's really true about the things that we're building and how we're building them. We can never be certain of success, however diligent we are, however carefully we plan, until we start interacting with reality. We are not certain that whatever it is that we plan is going to be correct. Progress only comes when we risk failure. Until, one of the kind of magic aspects, if that's not really the right term, but one of the magic aspects of the scientific method is that we learn most when our experiments fail. If our experiments are always succeeding, we're not really learning anything. They're just confirming our guesses. As soon as an experiment fails, that's the point where we go, that's not what I expected, and now I've got to come up with a new theory, and that's when I'm learning. So we need to take the risk to allow for failure to be experimental. So we learn most when reality does not match our predictions. Production is always going to surprise us. One of the things that I say in the context of continuous delivery is that you can never, ever prove that your software is good. You can never do that. But you can prove that your software is not good enough. However many tests you have, you always might miss something, so you can't prove that you've got all the test coverage. But as soon as one test fails, you know that your software is not good enough and you can reject it. This is the idea of falsification, which was kind of first discussed in the context of science in the 1930s by Karl Popper. And it's deeply important in our ability to learn and move forwards and explore with quality and confidence. So production's always going to surprise us, and it should. We should be taking sufficient risks to allow production to surprise us. If you think about all of the information that we have, all of the design thoughts that we have, the code that we've got, the tests that we have, the documentation that we have, our concept of the program, everything, all of it is really only our best theory so far. And we should be looking at ways in which we can improve that theory all of the time and refine it and deepen it and make it higher quality all of the time. So I think, I'm a little biased, but I think that continuous delivery is an example of such an engineering discipline. It's based on short feedback cycles. It's based on test-driven development. It's based on automation, hypothesis-driven approaches to design and development. And it uses tests as a falsification mechanism. It applies all of these 5 ideas deeply at the core of it. It uses feedback to allow us to learn and adapt and refine and deepen our understanding of ideas. But fundamentally, none of that matters as much as this. It's grounded in this. It's grounded in the ability to implement the scientific method. We want to make an observation of what's going on. We want to propose a theory that describes what's going on, and then on the basis of that theory, we're going to make a prediction. And then we're going to test that prediction, and that's going to refine the next observations that we make. We're going to observe what happens and refine our understanding. That's how humanity has made the explosive progress from essentially agrarian societies to the high-tech societies that we live in. I think that one of the things that's kind of happened during the span of my career is that we've got a deeper understanding of what really works in software development. And that's a big advance, but it's not yet evenly spread. So we need to start thinking and taking these sorts of issues seriously. As we start building more and more complex systems, we need to start optimizing for learning and for being able to fit ideas into human heads. Often when we talk about software development, we talk in terms of analogies. We talk about software development. I don't know if you've come across this one. It's been like a movie industry with directors and producers and actors and all that kind of stuff. And we talk about it being like production lines if we're thinking in waterfall systems. I'm not talking in analogies. I'm not suggesting that we should be like engineers. I am suggesting that we should take this seriously and we should be engineers. Let's start adopting science and applying it to our technology. That's the end of my talk. I hope you have a great day at the conference. Thank you very much. I think we're out of time for questions, but I'll be around for the rest of the day if anybody wants to talk to me about any of this stuff. Thank you very much indeed.
No questions?
If there are any questions, I'm happy to take some.
Oh.
There's somebody over there.
Up there.
Dave, thank you for your talk. It was very enlightening. Regarding the 5 features or the 5 I'm sorry, I can't find the
Attributes.
Attributes.
Properties. Yeah, something like
5
that.
attributes of software engineering. I think you're missing one,
yeah.
and it is supported by abstractions. It is true that when we develop systems, we split it in components. It is iterative, incremental. For each component, we iterate. It is iterative, yeah. But we also support our development on previous engineering efforts.
I think that you're correct. You're kind of stealing another presentation of mine. So these 5 things, I think, are kind of foundational ideas focused on the problem of software development from the perspective of how do we optimize for learning. I believe that what you're talking about is I've got another list of, I think there are another 5 things. There's another list of 5 things, abstraction being one of them, that is deeply important for the other part of the problem, which is how do you organize to be able to fit things into human beings' heads? And I think abstraction is that. And so you need both of these things to genuinely approach software development at its fundamentals. I think you need both to optimize for learning, and you need to optimize for want of a better term, modularity, being able to decompose ideas into smaller chunks so that we can kind of understand them and consider them and test them and develop them independently of one another. And so I would agree with you that that's missing from this presentation and is deeply important.
Absolutely, but the reason I bring this up is because when we don't take this 6th feature, 6th attribute into account as engineers, we end up developing stuff, looking at it as a production problem and reusing other engineering efforts, previous engineering efforts, without taking into account performance and efficiency. And we end up with Java stack traces of 400 lines for doing something very simple. So I think that's an important attribute to take into account for engineering.
Thank you. Yeah, I don't disagree. And there's none of this stuff. This is a short version of a slightly longer talk. And in the slightly longer talk, I talk about other attributes of this kind of idea. And one of the things that I think that we mistake is that we're looking for some kind of cookie cutter process where you can kind of just plug things at the one end and you get the same result out every time. It's never going to be like that, because the kind of engineering that we're talking about is deeply creative. We're talking about design engineering, and optimizing for design engineering is going to be unpredictable. So we need to optimize for learning and adaptation, and that's what this talk is really about. So you're still going to need very smart people making informed, intelligent choices to refine understanding in the context of what you're talking about. If you're optimizing to move very quickly in something where performance matters less, then you can get away with some of the things that you're describing. If you're working to build the highest performance system that you've ever seen in your life, you have to take the cost of abstraction seriously and measure it. But the engineering approach is still the same. It's about gathering feedback, measuring things, adapting to what you learn, and refining things, to my mind. But it's contextual. We got time for any more questions?
Hello. Thank you, Dave. Great talk. Big fan.
Thank you.
I have a question. So most of us here are developers or heavily involved in the technical aspects. So we're kind of sold on the idea of continuous integration, continuous delivery, continuous improvement on the technical side of things. My question is, do you have any advice for how can we get the rest of the companies that we work for involved in this in a kind of more rounded way? Having the whole company believing in the framework, working in this way, how can we improve things from within?
So the first thing is yes, I have lots of advice. My consultancy fees are available on request. no, but this is a deep problem. This is a difficult problem. I think what I perceive is what's happening is that the kind of the disruptive nature of applying technology the way that we do to driving business change is stressing the way that organizations organize themselves. And you're absolutely right. At the limit, you can't do the sort of stuff that I'm talking about in a vacuum. You can't do the stuff that I'm talking about in the middle of essentially a waterfall organization, which most large traditional organizations still are. And so, yes, you have to break down the barriers. You've got to start getting the changes. I spend a surprisingly large proportion of my time as a consultant advising people on management things rather than technical things. I'm a technologist, but it's deeply about organizational structures and culture as well as the technology to make this stuff work. There's wonderful arguments, ammunition that you can use in the work of Jez and Nicole Fosgren and Gene Kim in the Accelerate book, and in the Lean and Jez and Barry O'Reilly in the Lean Enterprise book. There's some good stuff out there. But it's difficult to make that change, and it's difficult to make that change from the context of somebody working in a technical team. The only thing that I can say is that you have to keep chipping away at it. You have to keep pointing out the non-rationality of some decision-making in other parts of the organization. And you have to do that in a way that's engaging and brings people in. And that's difficult stuff to do, but that's what you have to do. In the organizations that really adopt these kinds of ideas and take them on wholeheartedly, they don't look like traditional organizations. And there's some fairly good, deep technical reasons for this. If you look at stuff about complex adaptive systems, small world networks versus hierarchical networks and the performance of those sorts of ideas, there's some deep stuff going on here. But it's really true, it really works. So one of the interesting attributes of Amazon, for example, is that they are able to scale more quickly the bigger they grow. That's really, really deeply unusual. That's not what we think of as normal in most organizations. But it's what most organizations would aspire to. But they do it by doing some very radically different ways to the organizational principles for the organization. That's challenging for people to take on board and to adopt. But it's the kind of thing that you have to think about and you have to undertake. If you haven't already recommended it, I really strongly recommend the Accelerate book, The Science Behind DevOps, as one thing that kind of gives you some arguments at least to have with management in your organization. Thank you.
Okay, thank you. Thank you, Dave.
Thank you.